Every day, the AI landscape expands. We are faced with a continuous, chaotic flood of new paper summaries, tool alerts, and isolated concepts. Modern AI tools are exceptionally good at processing this volume. An LLM can instantly summarize a paper, extract a definition, or generate a concept map. But a summary does not give you orientation. When you just collect isolated facts, you remain blind to the underlying architecture. You don't know where a new AI idea actually belongs, what structural level it impacts, or how it might transfer to solve a real-world problem. To master this field, we have to stop treating AI as a static taxonomy of facts to be memorized and start treating it as a navigable cognitive space. Mastering AI today is a challenge of spatial orientation. This is the Cognitive Hologram. It is a structured, three-layer map designed specifically for navigating AI knowledge. The outer layer is contextual integration. This represents the external disciplines and real-world environments where AI capabilities are actually deployed and tested. The middle layer is the AI backbone. This is the stable map of deep learning systems, the actual terrain we move across. At the center lies the Transdimensional Learning Engine. This engine defines the precise rules for how we navigate the entire map. This central engine trains three specific cognitive movements: zoom, shift, and bridge. These movements separate active spatial navigation from passive reading. The first movement is zoom, the active traversal of abstraction levels. This abstract diagram shows the exact same river existing at three different structural realities. At the bottom, we have the molecular level. Here, reality is defined strictly by water molecules, chemical bonds, and energy exchange. Move up a tier to the watershed level and the structure changes. Now, reality is defined by tributaries, rainfall, and nutrient flows. Move to the top civilization level, and we find agriculture, trade routes, and cultural borders. The river is exactly the same, but each level reveals a completely different structure. Active zooming prevents us from getting trapped at the wrong resolution. If you stay too close, micro details obscure the broader system. If you stay too far back, grand abstractions hide the actual mechanisms. To apply this to AI learning, you must actively isolate the structural level of any new paper or method you read. You have to identify its precise location on the vertical axis. Is the paper presenting a low-level implementation detail, a module-level mechanism, a workflow update, or a system-level architecture shift? Pinning down the exact level instantly contextualizes the idea's scope, its limitations, and its relevance to the work. So the first practical routine is simple. When you encounter a new AI concept, you must always ask, what level does this AI idea change? The second movement is shift. Shifting means changing your analytical perspective while keeping the core object perfectly fixed. Consider a single, everyday object, like a standardized exam. Sliding into the student view reveals a reality focused on pressure, competition, and emotion. Shift to the teacher view, and those emotions disappear. The reality becomes a system of feedback, grading, and selection. Shift again to a sociologist or policymaker view, and the exam transforms into macro patterns of resource distribution, inequality, and institutional governance. The event is identical, but the view dictates what is revealed and what is hidden. Shifting prevents us from mistaking one single analytical perspective for the complete truth of an object. In AI, any single method or capability must be purposefully viewed through multiple distinct lenses. You can look at an architecture through a process view, tracking what happens chronologically. You can shift to a state space view, examining where parameters and outputs mathematically live. Or you can shift to a function view, isolating the actual capability performing the work. Changing the lens can reveal a completely different, highly valuable contribution hidden within the exact same AI paper. This gives us our second routine. When evaluating an AI method, ask, which view reveals the real contribution of this AI idea? The final movement is bridge. Bridging is the formal construction of a transfer interface. It is completely distinct from a loose analogy or lazy copy-pasting across disciplines. This priority board diagram illustrates the pure structural logic of medical triage. Triage is simply a mechanism for sorting priorities when time, attention, and resources are strictly limited. We can take this specific structure and bridge it into a completely new context, knowledge triage for AI research. The inputs change, but the logic holds. We calculate what must be read immediately, what requires expert review, and what is noise that should be ignored entirely. A successful bridge extracts the underlying problem-solving structure and leaves the surface content behind. In AI deployment, a capability is inherently useless in a vacuum. It only generates value when it is structurally connected to a real domain. Bridging follows a formal sequence. First, you identify the source structure and map it to the target context. Next, you build the adaptation interface. This handles the friction of real-world domain constraints and user workflows. Finally, you establish a feedback loop to scientifically validate if the transfer actually works. This exact sequence is how interdisciplinary thinkers successfully transfer useful AI architectures into fields like biology, design, or economics. The final practical routine requires you to ask, what structure can travel, and what interface is needed for it to work in a new context? These three movements form a unified operational protocol for integrating new AI knowledge. You evaluate the level. What level does it change? You evaluate the lens. Which view reveals its contribution? And evaluate the transfer. What structure can travel, and what must change to work? This protocol provides a methodology for reading, thinking, and designing within AI systems. The learning engine provides the required movements, but executing those movements requires a stable terrain to traverse. To use the engine effectively, we need to map the stable layer that sits just beneath it. Zoom, shift, bridge. How to move through AI knowledge. Next, the AI backbone.